Hey everyone, when we are talking about the systems in our course, we will talk about linear time invariant systems. These are the systems that we are going to bring for it the Laplace transform, and these are the systems that we are going to apply our inputs and analysis. So what is exactly linear time invariant systems, or LTI? Linear time invariant systems are systems that satisfy both the linearity and the time invariance property. In this case, called an LTI system. Yeah, what does it even mean? Linearity means that a linear system has two properties: superposition and homogeneity. So what is exactly these two? So superposition or additivity, which means that if the system has a response to an input, x of 1 is y of 1, if it is, and its response to x2 is y2, then the response to the combined input will be their summation. This is the superposition theorem. What do you even mean? So let's say we have an LTI system like this, and I give the system an input x of 1. So the output will be y of 1 of t. The same system, LTI, I subjected it into x2 of t. It will give us y1 of t or y2 of t. Okay, so two different inputs give us two different outputs. If I give the same system summation of the two inputs, x1 plus x2, then since it is a linear time invariant system, the output will be y1 plus y2. Okay, the summation of the two separate signals like this. And this is the superposition theorem for an LTI system. The second one is scaling or homogeneity, which is if the system responds to an input x of 1 is y, then ax1 as an input gives us ayt, the scaling factor. So for example, if you have LTI giving it an input of x1, so the output will be y1. If you give the input LTI, scale the input, let's say it is ax1, so the output will be ay1. So you can see that when I increased the input by a certain gain a, the output will also increase by a certain value a. That is the second property for a linear time invariant system. The last property, which is called the time invariance. It means that the system is time invariant if the behavior and characteristics of the system are fixed over time. So let's say at a time equal to 0, and we have this system, LTI. I give it a certain input x1, so it will give us a certain output y1. At a time equal to 100,000 after a very long time, if I did it the same LTI system, if I give it the same input after a very long time, it will give me exactly the same output y1. This one is called the time invariance. It doesn't change with time. Its behavior and the characteristics of the system are fixed. Now remember that these are the properties of a linear time invariant system. And these are the system that we are going to deal with in control system, because it is easy to deal with and easy to find or deal with them and find a relation between input and output. Does our system or our physical system is a linear time invariant system? No, actually every system has some kind of nonlinearity and some kind of time invariance. Also we hope that this design of the system or this linear time invariant system becomes sufficient for predicting the actual signals. Because as you know that in reality, if for example you give the system an input, it doesn't always give you the same output. There's some issues that can occur. And even if you scale the input due to its non-linearity of the system, it doesn't give us a y of t. And even the system itself, behavior and the characteristics will change with time, like friction of the system, like the machine becoming old, or any specific issue that can occur. So in control system, even if the actual physical system is non-linear, we often approximate it as a linear around a specific operating point to simplify analysis and design of our systems. So this linear approximation is typically valid for a small deviation from our operating point. Now, the transfer function of a system is the relation between input and output. So let's say it is the ratio between output signal to the input signal in the S domain with a zero initial condition. We assume that we have zero initial condition for our systems. So you can see that a relation between all the transfer function is y of s over x of s, where y of s is our output and x of s is our input. So you can see that in the time domain we have x of t, and we have transfer function of our system, representation of our system, and the output will be y of t. So y of t is simply x of t multiplied by the transfer function of the system, like this, because as you can see, h is the relation between output over input. So if I would like output, it will be transfer function of the system multiplied by the input giving to it, like this. In the Laplace transform in the frequency domain or S domain, complex frequency domain, x of t will become x of s, h of t will become h of s, and all of this will become s, which representing S domain. Now how can I convert this? By using this transformation, f of s equal to integration from 0 to infinity of f of t e to the power negative st, the extension of the Fourier transform. So let's say if I have an input signal, a DC input signal 1, or a step function of 1, that is the function in time domain. If you take this one and substitute it here, 1, you will get in the S domain, this solution will give us 1 over S. So the representation of a constant value is 1 over S. Representation of t is 1 over s squared. Representation of an exponential is 1 over s plus a, and etc. All of these sine, cosine, d over dt, and all of these different types. So the most important part is that you can see that derivative of a function in Laplace transform is s multiplied by f of s. Okay, so if I would like to replace d over dt, I will just say s, meaning derivative of the function f of s, like this. And integration is 1 over s multiplied by the function itself. So remember, this is very important as we will use this a lot. So let's say if I would like double integration, it will be 1 over s squared. Okay, why? Because it is an integration and another integration. Okay, and if you would like triple integration, it will be 1 over s cubed. Okay, similarly for derivative, if double derivative, second derivative, it will be s squared. Third derivative, it will be s cubed, and etc. Okay, that's why in the very beginning, when we converted the example of the non-separable differential equations, we used s and s 1 over s. Okay, now for example, if you have a unit step input, which means this one is 1 unit step input, like this, it goes from 0 to 1 like this, like this. That is a unit step input. Okay, Now this one is represented by a function of 1. So u of t, which is f of t here, is equal to 1. So integration from 0 to infinity e to the power negative st dt. By doing this integration, it will be the same exponential divided by the derivative of it, which is negative s, negative 1 over s, okay, divided by its derivative, negative s. Okay, and integration from and substituting from 0 to infinity, you will get finally 1 over s, which is this one. So this is how we get all of these relations from using this definition of Laplace transform.